Good day everyone, my name is Jerry Ayan Verinia and I will be discussing to you Research Methods for Engineers by David V. Thiel, Chapter 5.2, Two-Parameter Optimization Methods. So let's start. What is parameter optimization? It is the selection of parameter values which are optimal in some desired sense. It is also used to identify optimal settings for the inputs that you can control. Now, what is a two-parameter optimization method? The method is commonly used to optimize a design problem that are simply illustrated if only two parameters are involved. This allows the optimization process to be represented on three-dimensional plots, where the third dimension is the value of the cost function, C. A more in-depth discussion of cost function will be tackled in chapter 5.4, by the way. In many sport activities, a push or swing is a common characteristic. For example, a tennis racket swing, a cricket bat swing, a baseball bat swing, running, swimming, boxing, and ballet all have movements which start at rest and finish at rest. So let's take a look at the graph on the left side first before tackling the equations that you can see on the right side. So the x-axis is going to be our time measured in millisecond. This is, by the way, figure 5.1a. This is distance for the y-axis measured in meter. For 5.1b, that's going to be velocity measured in meter per second. And 5.1c is acceleration measured in meter per second squared. Now, I know for some of you guys, you are very familiar with the equation used for finding the distance, velocity, and acceleration, which is pretty similar to what you can see here. But the point is, we're looking at the graph on how, what is the relation of the graph to the equation. So as you can see here, let's say for example, we are going to swing a bat during a baseball. So the starting position looks something like this, and the end position looks something like this. Now, to find the distance, always you're going to start at a position, right? That's gonna be 0, and you're going to end at the maximum point or optimal position, as what you can see here on the graph. It looks something like this, although it does not necessarily show a linear pattern. It shows a curve pattern. Now, in velocity, as you all know, during the start and the end, or start and finish position, you're going to have 0 velocity. From point 0 to end point, which is 1 millisecond, are both 0 in this graph. And your optimal position or maximum point is going to be right in between. Not necessarily in the middle. Could be right here or right here. It doesn't matter, but it is going to follow this kind of pattern, curve pattern. Now, in acceleration, it's going to be different. Your optimal acceleration is always going to be right at the beginning, right? During your starting position, although you are not accelerating like literally, but if you're going to count the acceleration during the movement, normally the acceleration is at the optimal position or optimal point at the start and ends at 0, since you will be decelerating during that movement, then ends at a 0 acceleration. So follows this curve movement. So now let's take a look at the right side. Variation in A, 5.1a is the distance. Again, B is velocity, V, and C as acceleration, A, as a function of time, which is the x-axis. For a linear displacement following the equations, take a look. Dt is equal to L. By the way, this is angular displacement. Let's just call that L. Since we will be seeing that figure all throughout the discussion, and angular displacement is quite too long. So let's just say L sine squared times open parenthesis. This is the angular frequency, but let's just call it as omega, since again we'll be seeing this figure all throughout the discussion. So open parenthesis, omega times time, or t, close parenthesis. No need for me to explain further, since we will be I will be explaining to you how we came up with that equation later on. So equation 5.2, this is velocity. Vt is equal to derivative of d over derivative of t. That's equal to 2 times L omega cosine open parenthesis omega times time close parenthesis sine open parenthesis omega time, or omega times time close parenthesis. That is equal to L omega sine open parenthesis 2 times omega times time close parenthesis. Equation 5.3, this is our acceleration. At is equal to derivative squared of d over derivative of time squared. That is equal to 2 times L omega squared cosine open parenthesis 2 times omega times time close parenthesis. Okay, in sporting movements, the position of a limb, such as an arm or leg, or implement such as a bat, racket, stick, as a function of time, dt, can be modeled using a sinusoidal squared equation over the range of t is equal to 0 and t is equal to 1 equal to pi over 2 omega. As goes to show, we came up with this equation as I have showed you earlier, dt equal to L sine squared times omega t. Okay, where L, like I said, is the amplitude of the movement, or what is called as angular displacement. Omega is the angular frequency of the movement, and t is the time. Confining this example to linear movement, then d is the distance, and that is d is more than 0 but less than L, equal to 1. For time is greater than 0 but less than pi over 2 omega. This function is illustrated in this figure. This is what I showed you earlier. Okay. The acceleration at is given by, this is the equation I showed you earlier. Once again, at, hang on, maybe we skipped a part here. There we go. Equation dt is equal to L sine squared times omega t satisfies the requirement that the distance traveled changes monotonically from 0 to L, and the velocity is 0 at the start and at the end of the movement. Like I mentioned to you earlier, velocity is going to be at 0 during the start position and the end position. Say for example, when you're swinging a baseball bat. Differentiating equation dt equal to L sine squared omega t for the distance gives us the velocity vt, which is L times omega sine of 2 omega time, whereas t is equal to 0 and t is equal to pi over 2 omega. Then vt is equal to 0. This is shown in this figure. Okay, one more time. The acceleration at is given by the equation, as you can see here, 2 times L omega squared cosine cosine of 2 2 times omega time. The function in this equation is illustrated in this figure following this curve pattern. From these acceleration movements, a fitted curve will allow the determination of the constant L and omega, and so a complete interpretation of dt and vt. The objective is to find the best optimal values for d and omega, which are determined by a comparison of the function equation in function given in equation 5.3 and the measured data from the accelerometer. The numerical value to be minimized is called the cost function. In this case, the cost function of c of d and omega is the RMS value given by this equation right here, which is summation of a sub index or a sub I minus a times t sub I, close parenthesis, squared. Index is 1 to n. For a sub I are the experimental measured values at t sub I. A t sub I are the values determined using the equation 5.3, which was the acceleration, by the way. Here you go. And the n is the total number of sample points. Assume that the acceleration is sampled at 50 samples per second, such that is at 0.02 seconds intervals. The experimental data are illustrated in this figure. It follows a linear pattern. The new equation becomes acceleration time equal to 2 times L times omega squared, cosine squared times omega, open parenthesis, t plus t sub 0, close parenthesis. The acceleration a at times t equal to 0 and t equal to pi over 2 omega is not 0. This is physically not possible, as all time derivatives of dt must be 0 at t equal to 0 and t equal to pi over 2 omega. So there must be a lead time before the acceleration reaches its maximum values at the start and at the end of the movement. So for simplicity, the monotonic portion of the acceleration will be used in this example. Let's go ahead and discuss to you the difference between unguided and guided optimization techniques. So the cost function c must be calculated multiple times using the estimated values of L and omega until a minimum cost function c value is found. Optimization techniques can be either guided or unguided optimization. So now the unguided technique or techniques rely on a predefined strategy to determine the next set of parameters L and omega. A value of c is then calculated and compared to the previous cost function values. Let me remove my face for a bit. The algorithm terminates when all predefined values have been tested. The values of L and omega, which contribute to the minimum value of c, are the optimized solution to the problem. Okay, so guided optimization techniques use recently derived values of c to select, that is to guide, the next set of parameters L and omega, and cost function c is again determined. The next values of L and omega are determined from the previous values of c. The algorithm terminates when no further improvement in c can be achieved. This coincides with the optimal values of L and omega and the minimum value of c. The quality of the solution depends on a number of preset limiting conditions as yet unknown shape of the cost function. So here are the three differences. The range of the parameters L and omega, which is called the solution space. The step size of L and omega, which is the resolution. And the number of minimum values of c in the solution space. It is possible that there is more than one minimum value of C in the solution space. If so, there is more than one solution to the optimization routine. It is essential to locate the best possible solution which coincides with the minimum value of C. If there is no minimum value in the solution space, then the range of parameters must be increased, or one must conclude that there is no optimal position or solution. Okay. There are many optimization strategies. Some are based on biologically inspired strategies. We will not be discussing this. These are, for example, the genetic algorithm, ant colony, particle swarm, and some are inspired by physical processes such as simulated annealing. In the following subsections, 4 techniques are illustrated, which we are going to discuss since they are part of the 2-parameter optimization techniques. These are called sequential uniform sampling. This is an exhaustive search method in which all possible solutions are tested, meaning we are going to find a lot of values for the cost function C. Second is the Monte Carlo method, is a purely random search method, meaning we are going to set random numbers for the angular displacement L and angular frequency omega. Next is the simplex method and gradient method are based on vector calculus concepts. Okay. So here are the other optimization techniques or methods. There are many optimization strategies. Some are based on hang on. We have okay. So let's go ahead and continue with sequential uniform sampling. The most obvious approach to optimization is to test all possible values of L and omega. It is still necessary to choose the range limits for L and omega, or relatively small increments for both L and omega, and sequentially step through all possible values of both parameters in the solution space range. This technique is referred to as the sequential uniform sampling, and in order to explore and demonstrate the efficacy of the various algorithms, a full view of the cost function over the parameter range of interest is presented. So this is the sequential uniform sampling algorithm flow, figure 5.3. This is an outcome of the process of sequential uniform sampling. You set first the L values, L ranges and omega ranges, and increment them. Therefore, you have delta L and delta omega. After that, you're going to define the minimum values for L and omega. Once you're done with that, set the L as L plus delta omega. L plus delta omega. No, L plus delta L. Sorry about that. And once you're done with that, you can go ahead and continue. Set the omega as omega plus delta omega. Then you calculate the cost function C of L and omega. You save those numbers, and you can continue, see if the omega is at maximum. If not, you're going to return back to this step. But if you found the maximum value of omega, then you can go ahead and continue. Check to see if the L value is at maximum. If yes, you can continue. But if not, you can return back to this step, setting the L as L plus delta L. If yes, you can go ahead and select the L and W and omega, which give minimum value of C. And that ends your sequential uniform sampling. And you already found those optimal position for the L, omega, and the cost function C. 3 dimensions. So now the flow chart showed in the previous slide outlines the algorithm used for sequential uniform sampling. Commonly, the technique will be applied more than once. The first attempt should use a coarse grid with a large incremental steps each of the parameters. I'll show you, by the way, what a coarse grid looks like in the next couple slides. Once a possible optimized parameter range has been obtained, a smaller range with smaller incremental steps can be used to improve the resolution of the solution. There are flaws in this method of approach in that local minimum, by the way, the local minimum is not necessarily the actual minimum, but it is only a minimum in that particular curve. Okay. Values in the cost function might not be defined and investigated. It is possible that the best minimum cost function value will be missed if the initial incremental values are set too large for all parameters. So let's take a look at these graphs first. You can pause the video if you want to. Figure 5.4a is the mesh plot. Figure 5.4b is the contour plot. Okay. Now, figure 5.4 shows the cost function C results for all possible values for L in the range L is greater than 3000 or 0.003 but less than 0.3, with a step size of delta L equal to 0.003, 100 points, and omega in the range of omega is greater than 0.3 but less than 10, with a step size of delta omega greater than 0.3, which is 30 points. The offset time was set to t sub 0 equal to 0. The total number of calculations required for an exhaustive search is 3000. For problems involving a complex time-consuming numerical calculations, the total time to run the method will be very large indeed. So for figure 5.4a and 5.4b, show that the variation in cost function C around the optimal solution, which is the minimum value of C located at omega equal to 70 rad per second and L equal to 0.207 meter, is quite small for step size changes used for L and omega. I'll show you again the graphs. C values for all possible L and omega values in the range. Again, L is greater than 3000 but less than 0.3, and omega is greater than 0.3 but less than 10. The objective is to find the values of L and omega which coincide with the minimum value of C. Okay. You can pause the video right now to familiarize the graphs. Figure 5.5a is the mesh plot and figure 5.5b is the contour plot. By the way, the peak corresponds to the minimum value of C. This is our peak and this is our peak in terms of frequency, and this is our peak in terms of amplitude. An alternative presentation method is to consider the inverse values of cost function C. See figure 5.5a and 5.5b, which I showed you earlier. This is referred to as the fitness function and must be maximized to obtain the optimized solution. This converts the shallow minimum cost function C value to several well-defined peaks. The cost function C of L and omega therefore has several well-defined solutions but only one dominant solution. An effective optimization routine must ensure that the solution converges to the best possible and is not trapped in one of the local minima. Again, these are those graphs. Okay. The values of L and omega can be determined from the highest peak in 1 over C, or cost function C. The optimized solution, L equal to 207 0.207 meter and omega equal to 7 rad per second is plotted together with the experimental data in figure 5.6a, which is this graph, follows a curve pattern like this. Therefore, a good match is evident through visual inspection. Okay, so figure 5.7 shows the variation in C with every iteration following the sequence in figure 5.3. It is clear that at some point, the optimized values of L and omega have been passed, and yet the program continues to calculate every possible set of values. For this reason, this method of optimization is described as unguided. By the way, this is again, I'm showing to you guys the flow and how to do the sequential uniform sampling method. So for improved resolution of the fitted parameters L and omega, the offset parameter t sub 0 can be optimized. Figure 5.8, which is this figure, shows the sequential variation in C using the optimized values of L and omega and sequentially changing t sub 0, and an improved value of C is obtained. While this looks like the best possible solution, the individual optimization of parameters will not provide the best solution. This is because of the interdependence of the three parameters. In this case, the optimized solution must have an improved solution as all three parameters L, omega, and t sub 0 are solved simultaneously rather than independently. There is a significant relationship between omega and t sub 0. So for this reason, there is no certainty that the optimal values of L, omega, and t sub 0 have been derived accurately using this method. With t sub 0 equal to 0.008 or 8,000 millisecond, a new cost function minimum has been obtained, and so the optimum values of L and omega should be recalculated. The number of calculations required to optimize all three parameters using sequential uniform sampling becomes 300,000 if 100 values of t sub 0 are tested. In this case, the forward solution is not particularly difficult or time-consuming. However, if the forward solver is slow, for example, 15 minutes per solution, the total run for the optimization procedure will be very long. That is approximately 77 hours. It is clear that the optimization method will have improved accuracy when the sample intervals for each parameter are small and the range is large. This is the reason why alternative optimization methods are sought for multidimensional problems. So next, we are going to talk about Monte Carlo optimization. So Monte Carlo optimization technique is based on random selection of parameter values within the defined range. Figure 5.9, which I will show you next, illustrates the algorithm. For this example, the probability of randomly selecting values that are close to the correct value depends on the 3,000 options available. This is based on the range and interval used in sequential uniform sampling. The number of random samples, L sub I and omega sub I, tested with the cost function depends on the sensitivity and range of the parameters. So this is that figure. Again, this is going to be our flow for the Monte Carlo optimization method. You set the L and omega range and increment them as delta L and delta omega. Count is going to be 0. Once you're done with that, randomly select the L and omega values, and then you calculate cost function C, increment the count, and save those numbers for the cost function C, the L, and the omega. And is it the AND count after that? If it is a no, then you go back to this process. If it is a yes, select those L and omega for minimum value of cost function C. And then there ends your process for the Monte Carlo optimization technique. Okay, an inspection of 3,000 points in figure 5.7 reveals that less than 30 points, 1% of the total data set, have a logarithmic C is less than 2. Using a Monte Carlo data set of 2% of the population, that is 60 from a total of 3,000, the probability of obtaining logarithmic C is less than 2 is very low. Okay, so in figure 5.10, a simplex triangle defined in the two-dimensional solution space by the point L sub I and omega sub j, L sub I plus 1 and W sub j, omega sub j, and L sub I and omega sub j plus 1 is shown by the black dots. This is L sub I, omega sub j. This is omega sub j plus 1. This is L sub I plus 1. Is shown by the black dots. Depending on the cost function values at each of these 3 points, the point with the maximum cost function is replaced by one of the open circle position. If the search range for L and omega is restricted to ranges closer to the correct value, then the probability of gaining useful results increases significantly. Of course, this is only possible if an approximate solution is known. In this case, the Monte Carlo method is used to improve the accuracy of the solution. The Monte Carlo method is an unguided optimization technique. There you have it. So now let's talk about simplex optimization method. This employs a directed strategy to determine the minimum values of the cost function. The start point for L and omega in the range is selected randomly. The cost function for two adjacent points is calculated. The first is a delta omega, step in the omega direction from the start point. The second is a delta L, step in the L direction from the start point. Then these three adjacent points are called a simplex. In three-dimensional analysis, the simplex has 4 points, and in an n-dimensional problem, the simplex has n plus 1 points. The path towards the optimal solution is guided by comparing the cost functions for each of the 3 adjacent points in the simplex. From this information, a new point is selected by stepping the direction of the minimum cost function C value away from the position of the maximum cost function C in the simplex. This new point is added to the simplex, and the point with the highest C value is eliminated. This forms a new 3-point simplex. The process is repeated until no reduction in C is observed. Figure 5.11 illustrates the simplex optimization algorithm. Let's see. So you start with L and omega ranges again and set increments, again delta L and delta omega, and then randomly select the L sub I and W omega sub j. Once you're done with that, calculate the cost function of L sub I and W sub j, and cost function of L sub I plus 1 and W sub j, and cost function of L sub I and omega sub j plus 1, which are those 3 dots. Once you're done with that, replace the max C with the new values of L and omega. Find the new C minimum and C maximum, or cost function C minimum and cost function C maximum. If you're done with that, try to see if the C minimum is greater than the C, the actual C. If it is a yes, step the L sub I and W sub J to the L direction and omega direction, and then you go back to this step. If not, you save those numbers for L and omega, and that ends your simplex method. The algorithm can be written as follows. I will not be reading out everything here, but if you want, you can pause the video to familiarize or check the algorithm. But bottom line is the cost function is calculated for the new positions on the L and omega axis. The process is repeated until no reduction in the cost function is possible. The flowchart is given in figure 5.11, which I showed you earlier. And 4 typical paths are illustrated in the figure 5.12. Note that the algorithm defined in figure 5.11 allows for 6 possible new points only. There are only 3 possible directions of the path with positive and negative directional options. Movement in another direction is achieved in a zigzag pattern or path, and the progress towards the optimal solution is slowed. If the path is trapped in a local minimum, then the process terminates with a suboptimal solution. This is figure 5.12. Using 4 different starting locations, the simplex algorithm tracks through the solution space until a minimum value of cost function C is located. Note that the path can only take one of 6 possible directions, as you can see here. The start position of L sub I and omega sub J is selected randomly, as there is a possibility that the path will be trapped in a local minimum value. The complete algorithm must be run several times with different start position in order to increase the probability that the global minimum cost function is obtained. This corresponds to the best possible values of the parameters and the best fit for the experimental data. The speed of convergence also depends on the startup position, by the way. And there are many variations in the basic method of approach aimed at improving the speed of convergence. That ends topics for the simplex. Let's go ahead and discuss gradient optimization method. This method is similar to the simplex method, but uses a slightly more direct route to the solution by placing more emphasis on the relative values of the 3 points of the cost function in the simplex. The slope of the path through the solution space is calculated using the gradient vector. Let's just call this del C bar, defined by the equation 5.6. Del C bar is equal to del C over del L times X bar plus delta C over delta omega times Y bar, where X bar is the unit vector parallel to the L axis and Y bar is the unit vector parallel to the omega axis. This straight line path is the line of the steepest descent. The slope of the line M is given by this equation. M is equal to delta C divided by delta omega all over delta C divided by delta L. So the next position in the solution space is given by the new value of L, and the equation is going to be omega is equal to M open parenthesis L minus L max close parenthesis plus omega maximum. Okay, so the start position or start point for the initial simplex is randomly selected. The maximum C value at position L max and omega max for the simplex is defined at the start point. The value of C at the start point is then calculated using equation 5.8, which is this, since we are trying to look for the omega. The path follows a straight line defined by the gradient given by del C. Supposedly this should have a bar. Del C bar in equation 5.6, which I showed you earlier. That is del C bar equal to del C over del L times X bar plus del C over del omega times Y bar. When cost function C ceases to decrease along this path, the simplex is again defined at the minimum point and a new gradient vector is calculated. The process continues until no further reduction in C is obtained. The best solution for L and omega is identified at this point, forms the best solution. It is possible that the path can become trapped in a local cost function minimum. A flowchart for the gradient optimization technique is given in figure 5.14. Figure 5.15 shows the positional change in the solution space, and in figure 5.16 shows the convergence of algorithm. Figure 5.15 shows that the start point of L equal to 0.1 and omega equal to 2 results in a very large deviation in the first iterations, after which it rapidly converges on the solution. The start point at omega equal to 8 and omega equal to 9 follow the same path to the solution. The path which starts at omega 5.5 becomes trapped in a local minimum value. Let me show that to you right now. So here we are. This is the path or sequence that we are going to use following the gradient optimization technique. So we first again set the L and omega ranges and also delta L and delta omega, and then we randomly select the L sub I and W sub J. After that, we calculate the cost function C of L sub I and W sub J, the cost function C of L sub I plus 1 and omega sub J, cost function C of L sub I and omega sub J plus 1, and also the del C bar. Once we're done with that, we set the L as L plus delta L, calculate the omega and C. Once you're done, check to see if the C minimum is greater than C, or C is less than C minimum. If yes, we go back to this step, and if not, is there a change in C? If it's yes, we go back to this step, and if no, save those L and omega. That ends your gradient optimization algorithm. And these are those figures which I talked about earlier, figure 5.15 and 5.16. You can pause the video right here if you want to, and pause the video right here if you want to, so that you can understand what is talked about in this paragraph. Oops, let me remove my face, by the way. There we go. You can pause the video. Okay. In 3 of the 4 cases, the speed of convergence shown in figure 5.16 is faster than the simplex method. As with the simplex method outlined in section 5.2.3, which basically talked about the simplex optimization method, not all solutions result in locating the position of the minimum value of the cost function C in the solution space. It is therefore essential to run the algorithm a number of times using randomly located start positions. This can reduce the likelihood of the algorithm terminating in a local minimum. The optimal solution is that solution where the cost function is a minimum. Okay, so to summarize, the speed of convergence is significantly different for each optimization method, while sequential uniform sampling required 3,000 calculations of cost function C. The Monte Carlo method had a much smaller number of calculations but had a very small probability of achieving the optimal solution, while the simplex and gradient method converged to the solution more rapidly, but the number of calculations of cost function C was highly dependent on the random start point. The quickest solution was achieved by the gradient method in 15 calculations. With the optimal values of L and omega defined by the optimization process, the function d, or distance, is uniquely defined using equation 5.1, which I showed you at the start, at the beginning, the equation for finding the distance. From this, the maximum velocity can be obtained by comparison. A numerical integration of the acceleration data yields a velocity v with a constant, and a second integration to find the distance d results in an additional constant and a linear offset. The mathematical approach given by equations 5.1 and 5.3 is far more efficient. So that ends my discussion for you today about the two parameter optimization techniques or methods. Thank you so much. Once again, this is Jerry Ian Varinia. Thank you.